This is the lecture for Friday, January 25th, for Physics 492 and 802. We will be talking today about more nuclear burning in stars and supernovae. And these slides are originally written by Steve Daunt from the University of Tennessee. I've made a few small edits, but mainly his slides. Okay, we start off by talking about the elements that we see on Earth. So there are about 81 stable elements and 10 radioactive elements that we can see with non-negligible abundance on Earth. And so you may wonder where they come from. So here's a graph that shows relative abundances of different elements in the universe. You see lots of hydrogen, helium. You see peaks at carbon and oxygen, and we have neon, magnesium, silicon, sulfur. We have another peak at iron. We have some other peaks as well. So this is versus the atomic number. Okay, let's first talk about how carbon is made. We already talked about the formation of helium and the alpha particles. So we're going to talk about how some of the heavier elements are well, not so heavy yet, but some of the other elements are made. So once the helium is made, helium-4 nuclei, these alpha particles, the difficulty is that these helium-4 nuclei are quite stable in terms of the binding energy per particle. It's about 7 mega electron volts per particle. The helium-4 binding energy is about 28. Divide by 4, it's about 7 energy per particle. If you go from 4 particles, 4 nucleons, to 5 nucleons, there's actually no bound nucleus with 5 nucleons. There are bound nuclei with 6 nucleons, but the binding energy per particle is less than that of helium 4. You can go to 7, and again, there are nuclei, but there's nothing with binding energy comparable to that of binding energy per particle compared to that of helium 4. Again, 8, the same deal, nothing comparable to helium 4. Although beryllium 8 comes close, it's a resonance that's just barely unstable. Now then 9, once again, there's nothing with as much binding energy per particle. 10 also, 11 also. It's only until you get up to carbon 12 that you get a binding energy per particle that's more than that in helium-4. So if I remember from last lecture that the temperature of the sun is only a little bit less than 2 kiloelectron volts. So on the nuclear scale, that's actually rather cold. And so we cannot, there's not an easy path from going from 4 nucleons to 12 nucleons because all the other ones in between have less binding per particle, so you have to go up a potential barrier. So how do we actually get to carbon 12? And that in itself is actually kind of a neat story, this triple alpha reaction. What actually happens is that there are these two alpha particles. They actually combine and they can form then a beryllium-8 nucleus, which is an unstable particle or resonance. Okay, but this resonance actually having a resonance near threshold, near the energy for 2 free helium-4 nuclei, it actually enhances the reaction rate, but it's actually not enough to account for the amount of carbon in our universe. And carbon is very important, as you probably well know. Organic chemistry is based upon the chemistry of carbon and all the elements that are used in basically all life processes involve carbon. And so from the point of view of having enough carbon in the universe for life, it's important that you actually make some carbon, right? But it's actually difficult to make carbon. So as I said, this beryllium-8 resonance enhances a little bit the reaction for 2 helium-4 nuclei to come together. but it requires actually another resonance when we have our third helium-4 or alpha particle coming near the beryllium-8. It actually requires another resonance. This is an excited state of carbon-12 called the Hoyle state. And this state is actually very close to the threshold for the beryllium-8 and helium-4, and that actually enhances the reaction of the third alpha particle. And this is enough to explain the production of carbon-12 in our universe. In fact, Fred Hoyle was a theorist who predicted the existence of this excited zero-plus state. It has this positive parity and spin 0. It's basically the same quantum numbers as the ground state, but it's about 7 MeV, 7.5 MeV above the ground state energy. He predicted the existence of this excited state simply to explain how carbon's produced, because without it there would not be enough carbon. So it's kind of an interesting historical fact that he predicted the state before it was seen, and then thereafter experimentalists went out and looked for this excited state of carbon-12, and they found it exactly where he said it was going to be. Now, so once you've formed carbon-12, it can then do various things. It can combine with itself and fuse and form magnesium-24. This can go rather quickly. We can have carbon-12 actually fuse with helium-4. This can then produce oxygen-16. And this is actually a very important process where now the oxygen-16, which itself is a very important element for example, water. Without that, we would not have water. And so these types of reactions involve helium nuclei and helium-like or nuclei in the sense that they have an even number of protons, an even number of neutrons, and the number of protons and neutrons are equal. So that you notice we have helium-4 has 2 protons, 2 neutrons. Silicon-28 has 14 protons, 14 neutrons. Sulfur-32 has 16 plus 16 protons, 16 neutrons, and so on. So these sort of what you can call alpha-like, or sometimes they're called self-conjugate or alpha-conjugate nuclei, are actually made quite readily in these fusion processes once you've made your helium-4 and then you've made your carbon-12. Okay, so these alpha fusion processes are made in more abundance than the other elements processes. Now it keeps going along this chain until you get to iron 52, nickel 56. Okay, so this last nucleus in the alpha particle chain is nickel 56. Now this is, however, unstable, so unstable with respect to the weak interactions, and it decays after a few days to cobalt 56, which itself is unstable, but it takes a little bit longer time, and then that decays to iron 56. So now this iron 56 is the most stable nucleus, and so it neither fuses nor decays, it just collects iron 56. So these observations and this idea of helium burning and the formation of these alpha conjugate nuclei suggests a certain pattern to the brightness of these stars that produce these heavier elements. And I'm talking about higher mass stars. The lower mass stars never get this far along. So if you have a star that has just maybe a few solar masses, then it never really, like our star, would never really get this very far along. It would stop somewhere along, actually maybe even before this, getting to the carbon oxygen stage, but not getting very much past it, and that's it would end up then becoming a what's called a white dwarf star. But if you have heavier mass stars, several tens of masses, solar masses, then it can go all the way up that chain. And so this then gives us a prediction, what I was talking about before about the production of nickel 56 decays to cobalt 56, that decays to iron 56. If you see some explosion, a supernovae, this what's called a core collapse supernovae, are type. Well, we'll talk about the various types in a moment of supernovae. Then you can look at the luminosity, how much brightness you get in solar units per as a function of time, and you see you get a peak, and you get a fast decay, and then you get a slow decay, plotted versus years. And you can then make a plot of what would happen if you draw lines corresponding with the exponential decay of nickel 56, and then you draw another slower decay for cobalt 56. And you see that they kind of intersect here, these two decays, and so you would expect to see sort of this knee bend shaped curve in the luminosity. So in other words, these decays are powering the gamma rays that you're seeing. So each of these decays give you the release of energy that you see in light. And so that's consistent with sort of the knee bend that you see in these supernovae luminosity plots. That tells us that this is probably the nuclear physics that we're seeing, the production of nickel 56 and the production of cobalt 56 decaying into iron 56. So let's talk about what's going on here. So we're speaking about the end of a high mass star. So we're talking about, let's say, something like a 20 solar mass star, something about 20 times the mass of our sun. So this high mass star can fuse elements all the way right up to iron, and then after we get to iron, the fusion is not energetically favorable because iron then has the largest amount of binding energy per particle. So we have this sort of onion shell picture of what's going on with the star, this high mass star. On the outer part, the very outer part, you have the hydrogen, or the non-burned hydrogen. Then you have hydrogen fusion going on, and then you have helium fusion, then you have carbon fusion, oxygen fusion, neon fusion, okay, and magnesium fusion, silicon fusion, and so on. And then we have iron ashes. It's not burning anymore, so it's just the result of the burning process ends up as an iron ash. And so this, if you're thinking time scales, this 20 solar mass star will burn carbon. The carbon fusion will take about 10,000 years. But once the iron core is starting to be formed, it only lasts about a day. It's a very quick process thereafter. So you can see what's going on here with the binding energy per particle. I've shown this before last time, talking about the binding mass per particle, and this is the number of particles. So you see we have sort of peaks here at here's the helium peak, binding energy per particle. Here's carbon, oxygen, and iron is the most stable energy per particle. And anything beyond that has less binding energy per particle than iron. And so what's happening with fusion here in this fusion burning process, we're going down in this manner, releasing energy. But then once we reach iron, we've run out of fuel. Okay. And because the process runs rather quickly, it's sort of a explosive sort of end. So what's happening is the star is huge. It has lots of mass, so we have a lot of mass. And so we have stuff here at some radius. Let's say this is the center. We have something out here. It's being pulled in with gravity. So there's a lot of inward force. Now, because of the burning process, we have then an outward pressure that's balancing off the inward force of gravity. But now what happens is, all of a sudden you've run out of things to burn, and it's now just ash, iron ash. And so you have now then something that's no longer giving you pressure outwards. And so these guys here still feel the inward force of gravity, so they're coming in, and they're going to then essentially smash into this iron core. They feel a lot of this inward pressure. So what happens is that something interesting happens. These electrons that were sort of getting carried along with the protons because of the Coulomb attraction, they get very unhappy. They get very unhappy. You can think of it in non-relativistic terms. the kinetic energy of if you're thinking about the kinetic energy in terms of momentum, is p squared over 2m, where m is the particle mass. Now, the funny thing is that for a given momentum, the kinetic energy will increase as the mass of the particle decreases. So in particular, the electron has a rather small mass. It's it's 2,000 times smaller mass than the proton or the neutron. As a result, its kinetic energy shoots up very fast as we start going to higher densities with these electrons. So for a given density, the degeneracy, what's called the degeneracy pressure coming from this high kinetic energy, is much more severe for the electron. So in fact, as these atoms, these nuclei with their electrons being dragged towards the center, they get pushed in towards higher pressures. The electrons get very unhappy, and what happens is it actually drives this process. It drives the process where the protons and neutrons actually combine together through the weak interactions to form an uncharged particle, the neutron, plus the neutrino, and the electron neutrino that you get through the weak interaction. So you actually convert the protons and electrons into neutrinos. Okay, so now into neutrons and neutrinos. Now the neutrinos, they escape because they don't really interact with anything except through the weak interactions. But then the neutrons are then left over, and they are compressed together until this until the star really has a very high density. It actually starts to reach the density of an atomic nucleus, which is kind of cool. So what you have is, for these high mass stars, you end up with a protoneutron star in the core. So these neutron stars can have radii of 10 or so kilometers or so, but they have as much mass as the sun. So it's extremely dense. Now, this collapse is still going on. It compresses the neutrons further until they recoil an enormous explosion known as a supernova. Okay, so here's an example of a star beforehand. Somewhere around here, you don't see anything, and then all of a sudden it shows up, and it gives as much light as maybe thousands of other stars put together, maybe the whole sky put together. Okay, so this supernova, or supernovae for plural, is this incredible explosion. It's very sudden. It's not something that repeats. It's tremendous. It gives tremendous amounts of light. It's luminous. Okay, I mean light, obviously. And so you can then draw curves of the light versus time, and you can see that there's two different types of characteristic luminosity plots. One is a type 1 supernovae, where we have this sort of behavior like this. Okay. And then we have a type 2, which has a more interesting kind of a behavior, a faster kink, and then more of a plateau, and then another kink like that. Okay. Let's talk about what these different types are. So, as I said, the supernova is a one-time event. It happens, and then there's almost nothing left of the original star. Then there's type 1 and there's type 2. I told you about the different curves, and let's explain the physics behind each of these. So type 1 has a slightly smoother curve like this, and then type 2 has the fast behavior. That was actually more, that was associated with let me show you here. Type 1 is associated with something called carbon detonation. Okay, and type 2 is associated with the death of a high mass star. So type 2 is what we had been describing, and that gives you this sort of characteristic luminosity plot. Okay, protected. Okay, let's talk about type 1, the carbon detonation. This comes from a white dwarf star. So a white dwarf star has carbon-12, oxygen 16. Usually in some combination. So stars like our sun, or not very high mass stars, will burn, but they won't completely burn their carbon or their oxygen. Okay, and so they'll eventually stop, and they will just be happy as some white dwarf star, and we don't really see much of them because they're not shedding much light. Now, However, there is the work of Chandrasekharan, an Indian physicist who was interested in these white dwarf stars, and he came up with the observation that if you have these white dwarf stars, what's holding them up, there's this balance again between gravitational pull and outward pressure. And in this case, because we're not burning anymore, the outward pressure is actually something else. The outward pressure is coming from the fact that the electrons are fermions, and because they're fermions, they cannot occupy the same state. So if you compress them into a small space, you have to have a lot of energy, a lot of kinetic energy, so that these electrons occupy different sort of energy or momentum states. And so Chandrasekharan calculated this electron degeneracy pressure that you get for this either non-relativistic or relativistic electron gas, and compare that to the force that you get from a white dwarf with a certain mass. And he found that if you exceeded about 4.44 solar masses in mass for the white dwarf, that it was actually enough to make the radius of the white dwarf star collapse down to zero. He didn't actually know what happened in that case. We now know that what happens is some nuclear reaction will happen, and so this can actually be triggered in a certain way. Let me try to show you. In this plot here, suppose we have a binary star system. Here's a star that's nearing its end of its life. Well, it's approaching. It's not a high mass star, so it actually ends up becoming a white dwarf. Okay, and this white dwarf this white dwarf star is perfectly happy, except for the fact that there's another star next to it, and this other star now starts to expand because it's getting old and it's becoming a red giant star. It's doing more of its let's say it's carbon burning or reaching that stage, so it becomes enlarged and it starts shedding some of its mass, and it starts to accrete onto the white dwarf. Now, at some point, let's say the white dwarf was perfectly happy with the mass just, let's say, a little bit below the Chandrasekharan limits. Chandrasekharan is a friend of mine. Chandrasekhar limit. So now it pushes it over the Chandrasekhar limit. Then what will happen is that this will then collapse, and then there will be an explosion, what's called a carbon detonation. What happens is that the carbon fusion will then begin almost immediately throughout. It's just a very explosive process. Now, so that's type 1 supernovae. So type 2 supernovae is kind of different. I've already explained it to some extent. You have your helium, carbon, hydrogen, okay? So hydrogen is on the outside, then you have the helium, and then the other onion layers further in. And so then you start burning, and then you have the formation of your iron ashes at the center. Now, the stuff, though, on the outside doesn't know that it only knows the fact that there's no more pressure holding things in, so it starts falling in. But at some point, it bounces off the iron core, and then there's just some shock wave that's produced. And then now there are simulations. People, for example, here at MSU, people like Sean Couch, Luke Roberts, who do simulations of these things. And we can see how these supernovae, these core-type supernovae, explode. You form then a remnant core. Very often you end up with a neutron star, a proto-neutron star at the center, and then you have the shock wave, and you have all this supersonic sort of material streaming out. Okay. So these supernovae are rare, but thankfully there are many galaxies, so we can see supernovae throughout by the fact that there are many galaxies. But In our galaxy, there has not been one for 400 years. I'll tell you about the last one, but one of the last ones we've seen. Okay, so a supernovae called SN 1987A, that happened in 1987 as we observed it on Earth, did happen in the Large Magellanic Cloud, which is a nearby galaxy, so it was pretty close in terms of the grand scale of things. And its light curve was somewhat atypical. It looked something like this. It had some interesting features like that for the luminosity days. Okay. And so now, if we now look at 1987A, these days, we can actually see that there's a cloud of glowing gas that's now surrounding supernova 1987A. The fact that you see rings is due to the fact that you have some spherical sort of shell, and then when you look at something from a spherical shell, you can see sort of the edges of, the outer edges and get more contrast than let's say the center when you look at sort of the spherical shell. That's why you see these rings. And you can see different plots. Well, okay, so this is a rather old slide here from 1994 to 1996. But what you're showing here is that you can see a central object right in the center here that's forming. Now, supernovae in general leave behind remnants. So here's a much older remnant. So this is the Crab Nebula. So this is an explosion that's been recorded in history by Chinese astronomers from 1054. And you can see all the stuff that's been ejected from the supernovae, some cold collapse supernovae from the Crab Nebula supernova explosion. Now, you can look very carefully at this supernova remnant, and you can measure the light that's coming from these various places. And from the light, you can measure actually small differences in the frequency of the light, and that tells you how fast the light is moving relative to us, the observer, and that tells us the Doppler shift, and that tells us something about the expansion speed. Or the velocity at that point. And you can then sort of extrapolate back to figure out where the center of the explosion is. And if you do extrapolate back, and you can see something that appears to be a neutron star, a pulsar actually system, at the center of the Crab Nebula. A pulsar system is a neutron star that gives signals that pulses due to the rotation of the neutron star and the magnetic fields that you see. We'll talk about neutron stars next lecture. So we have this nice picture of the sort of cycle of stellar evolution. We start from some interstellar medium, and then gravity slowly collects stuff together and forms gases, and then we have an acceleration to form the stars into clumps, compact object stars. Okay, then you have the stellar burning. The stellar burning then eventually runs out of fuel, and then you have one or more types of supernovae that explodes and sprays all these elements throughout the universe, and then you have the interstellar medium, and then you can have this cycle going on. So if you have any questions, please send me an email, and as I mentioned before, send me an email summary of today's lecture, about 250 words or more, and you will get credit for your attendance. So thanks for listening.